So we just spent a whole bunch of time on latches because latches are your most basic sequential circuit. But the thing is, they're not actually used very much in modern digital design because they're very susceptible to noise. Now, why is this the case? Well, if you recall from our timing diagram, latches are what we call level sensitive. And what it means to be level sensitive is that any change in the input is going to change something in the output. So let's say if you were sending this set signal and all of a sudden, you had some sort of noise that caused a spike in the signal right here. So your set was supposed to be 0 this whole time, but because of some noise in your signal you got a spike. Well, that spike is going to get picked up in the output, which would cause Q to go high right here. So if Q goes high, that means that your whole circuit goes off, because now that Q is high, your set and reset condition are 0, 0, which means hold, which means you're going to hold for this amount of time. So this area right here is the incorrect operation of the circuit, all because of this noise in the signal that you got in the set signal. So latches aren't that great because they're very susceptible to noise, since they are what is called level sensitive. So that brings us to the next sequential circuit that we're going to talk about, which are called flip-flops. And flip-flops are basically the same thing as a latch. They have the same cross-coupled NOR or NAND gates in them, but they are edge sensitive instead of level sensitive. Edge sensitive. So let's start by looking at the most common flip-flop there is, called the D flip-flop, and then I'll describe why it's considered edge sensitive. So if we bring up good old World Wide Web here, here's a picture of a D flip-flop. Here's our cross-coupled NAND gate, which is very similar to the structure of the latch that we've just looked at. But now it also has what's called a gated latch by adding these extra AND gates in the beginning of the circuit to make this thing edge sensitive. And again, I'll show you what it means to be edge sensitive. So we have the input D and we have an input CLK, which stands for clock. So clock is what's going to give us the edge, and you'll see how this works. Alright, so let's further examine this D flip-flop. Remember, we described the SR latch with a circuit diagram and then also with a present next state table and an excitation table and a block level diagram. So let's go ahead and do that for the D flip-flop. I'll bring up the bamboo paper, new page. Okay, so our D flip-flop is going to be modeled with a black box diagram with an input D, output Q naught, which we show with a bubble. This is a Q, sorry. And we show a clock input with a little triangle here. Well, that's just horribly drawn. That's better. Okay, so there's our D flip-flop. Now we're going to look at the present state, next state table. We have our inputs D and Q. You might be thinking at the moment, well, what about clock? Well, I'll show you where that comes into play in a moment. And our next state, Q plus. So D and Q being both 0, 0, 1, 1, 0, or 1, 1. Our next state, if you went through and evaluated this whole circuit, your next state is going to be whatever D is. So no matter what your present state is, you're going to follow whatever your input D is. So here D is 0, so the next state is 0. Here D is 1, so the next state is 1. And we can write this equation, Q plus is equal to D. And we could write this in our excitation table, where we're going to show our state transitions, Q to Q plus, and then what inputs that cause it. So to go from state 0 to state 0, D has to be 0. To go from state 0 to state 1, D has to be 1. To go from state 1 to state 0, D has to be 0. And to go from state 1 to state 1, D has to be 1. Because again, the next state follows D. Alright, so let's look at a timing diagram of how this flip-flop works. This is how you'll see where clock and edge sensitivity come into play. Okay, we're going to look at page 349. Alright, so here's a timing diagram of the D flip-flop. Now here's your clock signal. The clock signal is just a very periodic signal that just goes low and high at a defined rate, and it goes on forever and ever. And the transitions from low to high are called edges. So here's a low to high transition for an edge, and here's a high to low transition for an edge. So this is a positively triggered flip-flop, which means that it triggers off the edge going from low to high. So Q, instead of changing whenever the input D changes, it's only going to change at an edge, which is why it's called edge sensitive. Okay, so let's say Q started off as 0. Remember now that in a D flip-flop, Q is going to be whatever D is, and you only evaluate it at the clock edge. So at this first clock edge, what is D? D is 1. So Q is going to become 1 because D was 1. So we make Q 1, and it's going to stay 1 until the next clock edge. So even though D is dipping down right here, Q is not going to dip down because it's only evaluated at the clock edge. Okay, so now here's our next edge. What is D at this edge? It's a 1. So Q is going to stay 1. Going along again, what is D at this edge? It's a 0, so Q is going to become a 0. Hold 0. This edge, D is a 0, so Q is going to stay 0. This edge, Q is a 1, so D is a 1, so Q is going to become 1. So this is what makes a flip-flop edge sensitive. And you can consider this sort of thing happening in D might be something like noise, where the signal drops down for a little bit, maybe when you didn't want it to, but it didn't matter because this Q is only evaluated at an instant in time. It's edge sensitive, not level sensitive. So D flip-flops are probably the most used type of flip-flop in digital design. Let's look at how we're going to model a D flip-flop in VHDL next.